Hello, my name is Haiyang, and I'm from NTNU Nanomechanical Lab. My supervisor is Professor Zhiliang Zhang. Today, I'm going to present our cohesive simulation results about the grain misorientation and size effects on hydrogen embrittlement in nickel. First, a little background. The present study belongs to the project entitled Integrative Nickel Alloys in Subsea Applications. And this is a joint project between NTNU and Untitled Solutions. At the present stage, our aim is to look at the hydrogen embrittlement of nickel in the grain level and try to improve the material performance with the help of the so-called grain boundary engineering technique. By optimizing the grain characteristics, this technique has the potential to improve the material performance to a large scale. But in order to implement this kind of technique, a premise is to have systematic knowledge about the grain misorientation and size effects. To get this, we perform the continuum level simulation with the help of the cohesive model. This model presents us with a phenomenological framework of modeling the correct propagation by allowing interfacial separation. And more specifically, we have the continuum elements here, and we insert a cohesive elements in between, which are governed by the so-called traction separation law, as shown in the middle. We can see here this TSL into two phases. In the first one, the cohesive stresses increase upon loading, but after the critical cohesive stress sigma C is reached, material degradation will be triggered, and the cohesive stress decreases. When the cohesive separation reaches the critical value, failure is detected. The cohesive zone model has been successfully implemented in the simulation of intergranular fracture. And the basic idea is to model the grain interior as anisotropic elasticity or crystal plasticity, and to model the grain boundary as cohesive layer. Then, upon loading, new fracture surfaces will be formed along the grain boundary, thereby giving the intergranular filling mode. Based on the same practice, we perform parametric study on this 4-grain nickel aggregate as shown here. As we can see, we have 4 nickel grains which are closely packed, and we model the grain boundary as a cohesive zone, whose parameters are determined based on the first principles calculations. And we model the grain interior as orthotropic elasticity, and further assume that the local directions of the elastic tensor corresponds to the crystallographic orientations of individual grains. For example, the local x direction corresponds to the 100 orientation. Then, if we rotate the elastic tensor, we are equivalently rotating the individual grains in the space. In this way, we keep the lower grains fixed, and we rotate the upper grains about the outer plane axis in a symmetrical manner. In this way, we can parameterize this misorientation angle theta in the range of 0 to 90 degrees. And to investigate the grain size effect, we further parameterize the grain size L in the range of 1 to 50 micrometers. For all the cases, we consider 2 scenarios. The first is the crack-free scenario. That is, we have a 0 value for A. The other is the pre-cracked scenario. That is, we have non-zero value for A, but we always keep a constant ratio between A and L. For hydrogen embrittlement simulation, we supply hydrogen to the outer boundary of this aggregate, and we leave the interior hydrogen free. And upon loading, we will allow hydrogen to diffuse driven by the hydrostatic stress field and redistribute to the local sites. For hydrogen diffusion, we consider 2 subcases. The first one is the steady state diffusion case. The second one is the transient case, which will be elaborated later. For all the cases, we apply the uniform tension at the top, and in the loading process, we update the cohesive strength, that's sigma C, from time to time, according to the hydrogen concentration. So, and this part is the results and discussion. During the cohesive zone simulation, we can get the nominal strength of the grain aggregate at the failure initiation point, and we plot the sigma F against the misorientation angle. So in this figure, we can observe a weird variation with the misorientation angle. And to make it more clear, we further normalize these curves by their corresponding values at the first point, which gives this figure. So we have the unity at the first point, and all the other points are steered by the value at the first point. Here it is easy to observe the trend of the variation. First, the strength will decrease with the misorientation angle, then it increases. And we have the minimum value at about 20 degrees, which is the most dangerous situation and should be avoided in the grain boundary engineering. It is also interesting to observe that the variation becomes less pronounced with the deeper pre-cracks, which indicates that the misorientation effect is somewhat suppressed with the existence of a pre-crack. And the size effect. We have two most representative cases here. We have a misorientation-free and most dangerous case with the 20 degrees, and we plot our nominal strength against the specimen size. Except for the case without misorientation or pre-crack, we observe obvious size effect in all the cases. And the general trend is that at larger grain sizes, we have a smaller material strength, which corresponds to the observation in the reality that grain refinement tends to improve the material strength. A step further, all these size effects could be adequately described by the size effect law for the polybrittle materials. And to do this, we choose three cases. The one, the crack-free situation with misorientation, and the pre-crack situation with and without misorientation. And we replot it in the log scale. So in this figure now, the slope at each point represents the strength of the size effect. So our first conclusion is that the size effect is not so pronounced, it's not so strong in the case without pre-crack as that in the cases with the pre-crack. And secondly, we can say that the data sets for the pre-crack cases are practically parallel to each other, which indicates that the size effect here is dominated by the pre-crack instead of the misorientation. Finally, these data sets could be divided into three branches. We have branch 1, which is a straight line at the large grain size. We have another straight line at small grain size. And in between, we have a transitional region. These three branches could be captured by the size effect law shown on the right. This law is developed based on the dimensional analysis. And as we can see, except for the red areas, all the other items are constant. So the size effect law is indicated directly here. We see that when our specimens are known, the grain size error is larger than critical value. It has been proved that the failure process zone is of a constant size. So we have the size effect here. And that means when error is far larger than L0, we have the branch 1 size dependence. And if it's comparable to L0, then we have the transitional region. And when the error is smaller than the critical value, the development of the failure process zone is confined. So we have another form of size effect, which corresponds to the branch 3. The size effect here suggests that if we are doing a nanomechanical test at the grain level to calibrate the decohesion parameter, then the calibrated parameter might not be a material constant because it is size dependent. And this law here might help us to bring it under control. So what is the situation at the hydrogen embrittlement situation? As aforementioned, this case is divided into two subcases. And in the transient diffusion case, we apply the transient diffusion where hydrogen has to move from the grain boundary step by step to the crack initiation point. That means the hydrogen distribution at failure might be different for different grain sizes because the distance for hydrogen to travel is dependent on the different grain size. The second case, we apply the steady state hydrogen diffusion directly at the beginning of the loading to all the cases. That means at the failure initiation, we have the same hydrogen distribution. And this figure plots the case of a steady state hydrogen diffusion together with the hydrogen-free case. From this figure, we can see an obvious degradation of hydrogen on the material strength. And more interestingly, we can say that the size effect, the trend of the size effect, does not seem to be affected with addition of hydrogen. But in the case with the transient hydrogen diffusion, the story is a little bit different. As we can see here, at the end of this size effect curve, the trend seems to be disturbed, which corresponds to the large grain size area. That means that the size effect law here is no longer capable of describing the size effect. So why is it? If we look into this equation, we'll see that at hydrogen embrittlement, not only the right region, but also the first item is variable, because this GF is related to the sigma C, which is now a function of hydrogen concentration. So we have to rewrite this equation to the following form. Now we have two variables. We have the sigma C as equation of the hydrogen concentration, and we have this original L-dependent item. So now the position of each point is dependent not only on the grain size, but also on the hydrogen concentration. And we believe that this explains the disturbance we observed here. And I think the general conclusion in this part is that with hydrogen embrittlement, the trend of the size effect law might or might not be disturbed, depending on whether we apply the steady state diffusion or the transient diffusion. That means if we want to capture this size effect, in the experiments, we should do really slow loading rate in order to guarantee the steady state hydrogen distribution. And I think here is some take-home message for you. Firstly, we observed the grain misorientation effect based on the cohesive zone simulation. And we conclude that maybe the misorientation angle about 20 degrees is the most dangerous. So in the grain boundary engineering, we need to avoid it. Also, the misorientation effect looks like suppressed in the existence of sharp grain crack. And also, the nominal strength is lower at larger grain sizes, which is the general trend of the size effect. And this size effect might be different in the hydrogen embrittlement, depending on the conditions for hydrogen diffusion. So that's all. Thank you.